Hi there, my name is Pedro Bertoletti, and me and Flavio will show you today the presentation entitled Using TCPIP sockets as IPC in NuttX to manage multiple LPWAN applications and one LPWAN transceiver. First of all, let's introduce ourselves. My name is Pedro Bertoletti. I work as technology consultant here in Instituto de Pesquisas Eldorado, and my colleague is Flávio Ipiranga. He works as embedded developer here in Instituto de Pesquisas Eldorado. We both work in Campinas, in one of the cities that Instituto Eldorado is based on. In order for you to know us a little better, let's talk about a little bit about Instituto Eldorado. Okay, Instituto de Pesquisas Eldorado, IPE for short, is one of the biggest research institutes in Latin America, counting today with more than 1,000 employees in 4 strategic Brazilian cities. IPE is based today in 4 Brazilian cities: Brasília, Porto Alegre, Campinas, and Manaus. As you can see here, left side of the screen, there's a photo of Campinas site of IPE. Okay, IPE works in state-of-art research and development solutions for the most of the major companies around the world in some key tech segments like oil and gas, telecom, IT, artificial intelligence, agriculture tech, and so on. Now, let's get started. We'll start showing you an overview of our presentation. In this presentation, we'll show you how you use the TCP IP sockets in NuttX as IPC to make it possible to synchronize or talk with multiple applications to send and receive messages from LPWAN connectivity. In this case, in this presentation, the LPWAN used is LoRaWAN. Our goals here are having a solid and reliable infrastructure to ensure IPC works fine for multiple applications simultaneously, having the possibility to host different IoT projects and solutions that use one single ESP32 and that has one single LP1 transceiver, and have the possibility to validate, test, and debug multiple IoT applications and solutions at the same time in a single ESP32, so we can test all of them under the same connectivity conditions, okay? Same signal strength, same antenna, same modem, same transceiver, and so on. Now, let's talk about IPC. For those who aren't familiar with this term, IPC stands for Inter-Process Communication. IPC is a mechanism that allows multiple processes to communicate with each other to get some synchronization between them. This allows processes to exchange messages, okay, or data with each other and get some synchronization, get some message exchange, and etc. IPC can be done in 2 ways. First way is by shared memory between processes, okay, and the second one is by exchanging messages from app to app. So in this second way, messages are exchanged between one app and multiple applications. Okay, so this is a more safer way to exchange data between different applications and processes. Here in our presentation, in our solution, we use the IPC method by message exchange. As you can see in the picture here in the right side, IPC works like a message bus, okay, allowing bidirectional communication between multiple processes or applications. This approach raises some requirements, like each app or each process must have a well-defined address, and all messages should have some kind of integrity check, okay, in order to ensure the content sent is the same content received. All these requirements are covered by TCP/IP sockets, okay, as we will talk a little bit later in this presentation. Now let's talk about how IPC and limited and shared resources combined can be a good thing, can be useful. IPC is a valuable resource in situations where a limited resources must be shared in a safe, controllable, and reliable way between multiple processes or applications. In this situation, the limited resource here is directly controlled by one central process or node, as you can see in the picture in the bottom side of the screen, which receives requests for all other processes or all other applications and processes them in a safe and reliable way. In the solution we are working on here in this presentation here in Eldorado, we choose to use LoRaWAN as LPWAN. So LoRaWAN connectivity is the limited resource here. In this case, if you look closely, IPC works like a star topology network. Okay, in this network topology, or in this IPC topology, the central node accesses these limited resources, in this case LoRaWAN, in a safe way, ensuring there won't be two or more simultaneous access to these resources. So the central node is that node that controls this limited and shared resource. Okay, this limited or this shared resource can be anything that it's not safe to share without any kind of control, like GPIOs, like transceivers, modems, and so on. Oh, also, there's a strong plus when using IPC for this goal shown here. The message exchanged between the apps or the process and the central node can carry more things than just the message itself. It can carry integrity checks, message flux control, and security check elements. So it strengthens the communication between the app and the central node. As we said before, in our solution, limited resources is LoRaWAN, okay? And now as LoRaWAN it's a limited resources, IPC used to control it, as we are proposing here, is justified. But why LoRaWAN is it's a limited resources? Why it should be controlled by a central node? Okay, let's talk about some key points and pain points about it. Okay, first of all, LoRaWAN transceivers usually have one communication interface, normally Uart. So if more than one process tries to access this interface at the same time, it won't work. So the access to a LoRaWAN transceivers must be centralized or must be controlled by one node only, by one app only. Second point is LPWAN connectivity plans usually offered in markets, and LPWAN protocols are designed to allow only few messages a day, which each message contains only few bytes. I'm talking about 10, 12, or maybe 20 bytes in most cases. So this should be controlled, the amount of messages, the volume of data sent, okay, and received, in order to make sure connectivity plan will last for the desirable amount of time, for a month, for example, and ensure all messages are sent correctly. So this technique to use IPC as a control for this LPWAN resource ensures LPWAN doesn't run out before it is expected. Okay, so it ensures LPWAN connectivity will remain until the end of the time period it must be. And finally, access control. LPWAN modems and transceivers configuration parameters are a little bit tricky to adjust, mainly considering its relies on where the transceiver is in the signal strength, SNR, and etc. So if some app or some process tries to change configuration, if it has this possibility, troubles can be, we'll see troubles, okay, we are in trouble. So to avoid problems in connectivity due to misconfiguration or something like that, it's mandatory that the central node or only one node, one node in the network controls the LoRaWAN transceiver and configures it. Okay, so this is mandatory for a good connectivity usage. Well, as we said before, we use the IPC to ensure some security, some safe in our communication. Okay, so we are talking now about TCP/IP sockets. Why to use TCP/IP sockets in IPC? Okay, first of all, no additional message integrity verification is needed because TCP/IP already uses 16-bit CRC. So some protocols, some industrial protocols, for example, like Modbus TCP, relies on that too. So as long as TCP has has already the integrity check, so no additional message with integrity verification is needed. Second point is communication and addresses are well defined by design. TCP/IP works with IP addresses and ports, so it ensures message will reach its destiny correctly. Okay. The third point is TCP/IP sockets are already widely used in C or C++. There's a lot of libraries, APIs, software, piece of softwares that use TCP/IP sockets now. So it's not hard to establish a socket connection and works with it. It's not new. So as it is widely used in C or C++ programming language, so the developer will have no troubles to integrating it into an application or a process. The next point is some standard and very well-known protocols can run over TCP/IP socket. Okay, like I said before, Modbus RTU. So if you wanna run Modbus RTU into this very proposal we are showing here of IPC using TCP/IP sockets, it will work. Okay, so this is a really good advantage considering some very specific applications like industrial applications in Modbus RTU. Next point, IPC will run on a local network, in this case, or in this presentation. So every tool to analyze and help to track bugs or track data in TCP/IP communication can be useful when debugging this communication. So if you sniff the communication using Wireshark or something like that, you can debug or can track the communication and maybe get some success to debug or to fix some tricky bug that is happening there. In the case of application has some bug or something like that. And finally, in the case of NuttX, it fully supports TCP/IP sockets. So putting it all together, we can see that TCP/IP sockets are really useful to be used together with IPC, and this combination is very good for this goal.
Now I'll talk a little bit about the hardware used in this project. One of them is the ESP32 dev kit. So this is the main board of the project. and we choose this board because it's very well supported by NuttX and also very known by the community. Another point that's very good about this board is that it's very easy to find in the market and also very cheap one for what this board offered to the developer. So this was the main reasons that we choose this hardware. Besides that, me and Pedro also have this same board, so it makes it very easy to communicate about the tests or the development, since we have the same hardware. And besides the main board, we have the LoRaWAN module that we use to communicate to the LPWAN. So here you have some specification about this hardware. And note that we have two classes that this hardware supports. In our project, we implement just one, the class A, because this is the one that's mandatory by the LoRaWAN specification. And the other point that we need to pay attention here is the baud rate, because in the next slides I will show to you about some configurations and you need to use this one at the Uart interface that we choose in the menu config. Here we have the both hardwares we use in this project. So we have the ESP32 board and the LoRaWAN module. And we also have the connection that you use between them. So we need the data communication, that's basically the GPIO 23 and GPIO 22, that's the Uart communication. And besides that, we also have the powering GPIO, so that we're connecting the ESP32 board also. To reproduce this project, first we need to have a NuttX environment working. In our microcontroller, in this case, the ESP32. So we have this link here. In this link you'll find a tutorial made by Sara Monteiro. And in this tutorial you have some steps that you need to make to flash the NuttX OS in the microcontroller. So by the end of the tutorial, you should have a completely working NuttX environment and you can access the system by using the terminal. So after that, you should do the second step, that is configuring the network of the NuttX environment. So in the tutorial that I mentioned before, we used the NSH configuration. So in our project, we need to configure some network features. To do that, we use the net NSH configuration. In the first time we tried to configure these network features, we had a lot of problems and a lot of trouble because we are not sure about what config we need to use and what we need to enable, what the parameters. After we find out this configuration, the network features was a lot of easy to configure and we just need to use the net NSH option. So after that, we also need to do one more configuration related to the network. Since our server and client are in the same hardware, we need to use the local loopback feature. So to do that, use the command make menu config so you can enable this option. Here you have an image that demonstrates to us where is the option of local loopback in the menu config. So if you access the network support option and after that the link layer support menu, you show these options to you. So you just need to select the option in the head arrow. Since we use a server application in our project, it will be very helpful to make this application start together with the NuttX OS. So to do that, we can use a feature in the NuttX that is startup script. So to understand better how this works, we have this link from the official documentation that will explain better about this procedure. And after doing this step of configuration, we also need to enable some features in the menu config. So now we have two images, and one of them is about the file sys that you need to enable. In this case, to this feature, you use the HOMFS, so it's really on file system. And besides that, you also need to enable the startup script feature. So in the right image, you have the support to run FS startup script. And beside that, in our case, we choose to use the architecture-specific path, so we also enable this option. In case that you don't want to do this kind of configuration or had some problem following the documentation, you also have another option that is to use this to call the server application in the NuttX terminal after the NuttX is working and you have access to the terminal. So you can use the name of the application, and after that you put the ampersand symbol, similar what you can do in the Linux, so the server application will be running background. That way, after that, you can use the client application, and that should work the same as having a startup script. Besides the network configuration and the startup script configuration, we also need to configure our Uart interface to communicate with the LoRaWAN module. So to do that, we need to enable some features in the menu config again. And first of all, we need to enable the Uart in the ESP32. So in the right image, we have the menu that you need to select. So going to system type, and after that ESP32 peripheral selection, you should have something like that. As you can see, we have the Uart and the Uart 0 and Uart 1 selected. So Uart 0 to debug and Uart 1 to communicate with LoRaWAN module. And besides that, we also have to configure our pins, so our GPIO pins. So in this case, we use 23 and 22. And finally, you also need to configure the baud rate. To communicate with our module, you use 9600 because the rate that you have in the module you are using. We also can see that we have more than 2 Uart interface. So if you need or want to use the Uart 2, you probably will have some compiler error, because in this version of the project, we can just use the Uart 1. So if you want to use another interface or are using another board, so take care about this part, and you need to adjust some parts of the code. And now finally have the best part of this presentation, that is the demonstration, which will be presented by Pedro, and Pedro will show to you guys our results and you'll explain a little bit about the code.
Now let's take a look at a demonstration of using TCP socket as IPC in NuttX operating system. First, it's important to say that the demonstration we'll show here has comprised in 2 different parts. One client, which demonstrates the process that needs access to LoRaWAN connectivity, and one server, which demonstrates the central or control node, which controls the access to LoRaWAN connectivity. Okay. Remember, the server part is the one part that actually controls the LoRaWAN transceiver. In this demonstration, use TCPIP sockets as IPC. The client requests the server to send 2-byte message via LoRaWAN on a short message to test it, and server handles it and gets back to client the response if a downlink message is available or not. Well, the message exchange between the server and the client are formatted in this custom protocol, which you can see here in this struct. The first field of this struct, or the first field exchanged in this message, is the opcode. The second one is a message size, and the last one is the payload itself, the message, which has at maximum 12 bytes and must be X string formatted. Well, regarding location of these applications, here are my NuttX environment. We have here ASP.bins folder, which has the bootloader and partition table binaries, and here the NuttX itself, and here the apps folder, which has the apps for NuttX operating system. We put this example, the client and server part here into examples. The client is named as client TCP and server is named as, let me check, servidor TCP. Okay. Now let's take a look at the client source code. Let's start with it. First of all, as said before, the client consists of a process or an application that needs LoRaWAN connectivity to send and receive data packets, messages via LoRaWAN. In this case, the client tries to send a 2 bytes message, a short message to test, every 15 seconds. Okay, it's crucial to mention here that is just a demonstration. Okay, and in practical terms, this is not cool. In real world, due to connectivity plus limitations, we are not able to send message at this rate. So keep in mind this is just a demonstration. Okay. Getting deeper into the code, here we have the main function, and the first thing it does is to get the arguments passed through by the command line or by its calling. Client source code, client project here receives the server IP address via arguments. So if this IP address is missing, the application must be closed, okay? Because there's not enough parameters. Then, if the client IP address is passed here, the client source code tries to create a client socket, okay? And if in case of success, it tries to connect to server socket and fill the address structure, okay, with the IP address passed before. If everything until here goes okay, the software enter is in the infinite loop, which is constantly send server some data and get its downlink message or its response from LoRaWAN transceiver. So it's important to mention here, the first thing to do before sending messages is to format them into this custom protocol we created. So we inserted here an opcode. The opcode U is the opcode for uplink message. The protocol message size is 4, and it's 4 because the message passed is 0102. It's an X string formatted, so it has 4 bytes long, so message size 4. Then the message is sent through the client socket to server, and if some bytes return, it waits for some bytes for a server response, and if it has a successful return, it prints, it parses the message returned, it prints it to a screen for debug, for verbose debug only. This is all the client code does. As can be seen, client source code is very simple and has no control over LoRaWAN connectivity as desired. So the server part is responsible for interacting with LoRaWAN transceiver, with LoRaWAN modem as desired. Now let's proceed to server code. Unlike the client, server gets no arguments, as you can see here at the main prototype. And also, this code, this server code, is automatically started as background process when NuttX boots, when NuttX starts. So the first thing the server does is to configure LoRaWAN credentials, as you can see here. Obviously, I jammed my credentials, so you can put your credentials, your own credentials here. And the credentials needed are application session key, network session key, application EUI, device address, and channel mask. The channel mask is it's a mask that informs LoRaWAN transceiver which channels should be used. And the channel mask here is also configured for Brazilian channels, for Brazilian allowed channels for LoRaWAN. So if you are not in Brazil, maybe this will change. After LoRaWAN transceiver configuration, the software proceeds to creation of server sockets. Okay, so if it goes okay, the address structure is filled and socket is bind operation starts. Okay, as you can see here, and after bind, it tries to listen for the incoming connecting, the pending connecting from client socket clients. As you can see here, the maximum pending socket clients connections defined here in this software is 20. So up to 20 socket clients connections or attempts to connection, it's okay. If it can handle with can handle 20 socket clients here. If everything goes okay until here, it starts in an infinite loop where it keep waiting for new connections, new client sockets connections, and if this connection is successful, a thread is instantiated for each client which connects. So each client is instantiated to a thread and handled in a separated thread. Okay, this thread is described right here. All this thread does here is it listens, it is waits for data coming from client. Okay, if data has been received, this data is forwarded to the deeper layers of the software. We'll describe it a little later, and the message is sent over LoRaWAN. When it gets back, when the message is returned, when the message is returned, it prints a status message of what happened here. Okay, so if the message size is less than 0, everything got wrong. Okay, otherwise it means the data sent to LoRaWAN has occurred successfully. So we can print how many bytes has been sent in a response to server, and goes on. So this while true or while one remains executing while connection is active, is working. If read functions returns invalid number, meaning connection has been gone, like 0, nothing has been received, or negative number, it means disconnection has been detected. So it terminates the thread, and this client no longer exists in server anymore. Now let's get a deeper view of the middle layer, the layer between this server main code and the deeper layer which deals with Uart and LoRaWAN transceiver. This layer meant was the protocol.c. This layer is responsible for taking the client request, parsing it, okay, accordingly to its opcode, and sending to the deeper layer, which is this. We'll get a little later, the message received from client, and take it, send it over LoRaWAN, and also it knows, it gets if some downlink message has been received. And after that, it formats a response message to be sent to the client by server code. And this message is also formatted in our custom protocol and has an opcode. Here it's downlink opcode. It has a message size. It's according to how many bytes has been received from downlink message in the deeper layer. And finally, the message itself, formatted in X string bytes, okay? Finally, the last layer of server code is the Uart LoRaWAN layer. This is represented by this source code, Uart underscore LoRaWAN underscore layer dot C. The source code handles all Uart data exchange between LoRaWAN transceiver and ESP32. And the main function in this module is this. All this do is clear buffer, receive buffer, send the message over LoRaWAN, and waits for some time to a downlink message be received. And it gets everything back to the middle layer, which gets everything back to server. So server has three layers: the main layer, the middle layer, which parses the client request, and the deepest layer, which exchanges data, which talks to the LoRaWAN transceiver itself. Now let's take a look on how it runs on a ESP32 board. I have here at my side a demonstration hardware plugged in to my computer, so I will access it via PicoCom software. Here we are at NuttX terminal, and the next thing I'll do is reset the board, so you can see the verbose debugging coming from the server side and have a real good idea of what's going on. Okay, I'm resetting it. As you can see, there are some verbose messages coming from the server side. Channel mask is configured, network join method is configured, and credentials and everything else. And now server is listening for new client connections. Here at the board we have a software called client. This software is the client, okay? So I will call it. First of all, the server here is running as a background process, okay? So let's run the client, passing as argument the loopback IP. So every data will exchange it here in the local network created inside the ESP32. As you can see, client connected to the server and send some data to be sent over LoRaWAN. Okay, this cycle will repeat every 15 seconds, as you can see some seconds from now. Let's wait some seconds. Here it is. It sends again, and if you take a look at the LoRaWAN cursor we have here, we can see data is being sent. Okay, so the LoRaWAN communication is working as desired. Flav and I would like to share our contact information. As you can see here, our email addresses. Please, if you have any questions after this presentation, feel free to contact us by our email shown below. Flav and I would like to thank you very much for watching us. Please, if you have a question, feel free to ask us now.